All right, can you hear me? Yep. Well, let me start by thanking the organizers, of course, for inviting me to come here. It's always great to be back home, especially if I get the chance to speak at such a nice meeting. So I'm very, very grateful. So I want to present some results that came out in the last couple of years in collaboration with Gary, who's here, and Arthur, who's here, and also Billy Cottrell and Thomas Michał from Wisconsin and from Heidelberg. And they have to do with the weak gravity conjecture and trying to prove it, approaches to giving evidence from them, as we've heard several other approaches in this conference. So motivation is not going to be anything new. It's already been said. I think it's very similar in spirit to, in particular, what Gary said in the introduction of his talk. We have a nice set of conjectures that we expect that string theory and more generally theories of quantum gravity, well, any theory consistent with quantum gravity will satisfy, and they are actually intimately related. We've seen some newer connections in this conference. But we expect them to hold not just because, well, to have a motivation beyond just being true in string theory examples that you can scan, but we expect them to have a motivation purely from quantum gravity considerations, that they are consistency conditions required for an effective theory to be coupled, to be allowed to couple consistently to gravity. And this program of trying to prove or derive the Swampland conjectures from purely quantum gravitational considerations, I think it's very important because it will show how general these conjectures are, if they hold in full generality, and in particular, what form do they take? What is the precise definition of this conjecture? And this is very important if you want to actually apply it to phenomenology. If you don't make precise the conjecture, you will always find loopholes, and someone will come up with a model that you cannot really rule out because you don't have the precise definition of the conjecture. So in this sense, it's very important to track down what are the motivations from quantum gravity of all of these conjectures. And I think, and it's shared by many other speakers, that the weak gravity conjecture is one of the most approachable ones, because we expect it to encode consistency conditions that relate to black holes and their entropy and cosmic censorship and other issues. So this is what I'm going to do as well. I will not make, I think other speakers have made very interesting claims and probably stronger than what I will give, but I want to add my little point of view on some of or approaches on some of these conjectures. Well, the weak gravity conjecture, we know, it just says that in any theory of quantum gravity with a gauge field, you have to have objects in your spectrum that satisfy such a type of relation, that the charge over tension is bigger than 1, where 1 is the charge over tension of extremal black objects. And in particular, I'm writing here tension because T of P, because I'm interested not only in the weak gravity conjecture for particles, but also for p-dimensional objects, more in general. And I think, in particular, p equals 0 corresponds to axions and instantons, and it's one of the most relevant for phenomenological applications. So it's very interesting to actually address all of the forms from different perspectives. So this is the outline of the talk. First of all, I will address one approach in considerations of black hole entropy to the one-form weak gravity conjecture, namely to particles and gauge fields. It's a little bit different from what Raymond and Gary talked in their presentations. Then I will move on to the zero form, the axion form of the weak gravity conjecture, and bring about a topic. I'm not going to give new results, but I think I want to raise concerns about Euclidean wormholes that I think could be very interesting in future explorations of the weak gravity conjecture for axions. And if I have time, I will also comment on the two-form weak gravity conjecture which can be approached by considering axionic black holes. I'm always going to stick to 4 dimensions here today. So in principle, these things could be generalized to more dimensions, but I want to consider only 4 here. Yeah, they are dual to each other, but what I mean I'm always also going to talk about the electric version. So in a sense, it's the electrical spectrum of the theory. When I talk about the 0, I'm going to talk about instantons. When I talk about the 2 form, I'm going to talk about strings. So not only was my motivation similar in spirit to Gary's motivation, but my slides are surprisingly similar in particular. So that's what happens when you have a collaborator and you share a Dropbox folder with all your talks. And you work hard on preparing some nice pictures. So anyway, you may have seen this before. Apologize. So why do we expect that we can approach the weak gravity conjecture using black holes? Well, the weak gravity conjecture is not so dissimilar to the no global symmetry conjecture. And for no global symmetries, one can argue that one has a problem with remnants. One can construct black holes that have arbitrarily global charge, and these, since there's no gauge field, these just behave as Schwarzschild black holes. They decay until they become Planckian or sub-Planckian, and you have an infinite number of them because they have an arbitrary charge. And this has been argued to lead to all sorts of problems with entropy bounds, for example. Now, something similar you could argue that happens when you have a weak gravity conjecture theory, namely if you take a gauge theory and send G to 0. In the limit G equals 0, you recover a global symmetry, you would expect these problems to arise as well. And you can try to play the same trick. What happens if you send G to 0 is that your particles becomes sub-extremal, and instead of repelling each other, they attract each other. So if they attract each other, I can form bound states, and these bound states will be exactly stable. So I can make a tower of exactly stable bound states. However, the difference with the global symmetry case is that these grow in size and mass. So it's not clear that the same arguments that, in particular, Susskind used to dismiss the remnants would apply to this theory because you don't have a finite mass range with an infinite number of states, but you have an infinite states in an infinite mass range. So it's not obvious that this tower of states is problematic. In particular, in principle, it doesn't look like it's going to be problematic if all these states satisfy the entropy bounds, that the entropy of these states, the number of states, scales like the area. All these arguments would not apply. Furthermore, we have seen that in string theory and supersymmetric theory, BPS states are stable, and there may be an infinite number of them, and that's not problematic at all. So one would like to understand whether there's a motivation of requiring these states to decay as the weak gravity conjecture, the strict weak gravity conjecture, argues for. And one thing to notice is that if one considers entropy of these bound states, if you consider BPS states, these objects would feel no force. I mean, they only have velocity dependence forces. So the thermodynamic behavior of a bunch of, if you put a large number of particles that don't attract each other nor repel each other, you have BPS states, you can model the thermodynamics of such a system. And in fact, it's called a Wormholes soup, and people have argued that a bunch of extremal states that don't feel a force between them, only velocity-dependent forces, they actually reproduce properties, thermodynamic properties of black holes. So in principle, by considering microscopic states with a large number of BPS supersymmetric states, you can actually argue that you can reproduce microscopically, for example, area loss of entropy. However, if you take this type of objects that do attract each other, there's no hope in reproducing that. They will attract each other. You've put enough of them, they will attract each other ad infinitum, and there's no bound state. You cannot compute an entropy. You will hit a singularity. And unless you put a UV cutoff in this system, you will not be able to compute something like an entropy. And in fact, if you put a UV cutoff, your entropy that you try to compute microscopically would be UV divergent. So this seems like a key difference between the BPS systems that we know are fine in string theory and these systems that would be allowed if the weak gravity conjecture was violated. Now, what we would like to do is to try to address this issue and compute the microscopic entropy of systems of mutually attractive particles, but that's way out of reach. We don't know how to do that, and why? Because if you include gravity, when these objects come close enough together, they form a horizon, and then you don't know what's happening. Usually what you do is you say, well, these have formed a horizon, so let me just say that the entropy of this system is just the area, just the Wittgenstein-Hawking area, Hawking entropy. And then you hope, well, microscopically, somehow the system will reproduce this entropy. But that's like giving up on trying to give a microscopic definition of the entropy. So we would like to address this problem, but we don't know how. Perhaps it's impossible if the weak gravity conjecture is true. There's no system of subextremal particles that exists consistently. So what we try to do is something much less much more conservative, is try to take an extremal black hole in a theory of Einstein-Maxwell and compute corrections to the entropy of an extremal black hole. So you are given already an extremal black hole and try to compute corrections from loops of particles, in particular from loops of charged particles, but subextremal, so the ones violating the weak gravity conjecture. So we set up to do that. It turned out to be a super involved computation, very risky. It had many pitfalls. We fall in all possible pitfalls that the equations pose us, but I think we reached a consistent result. In the end, it's not too exciting in terms of the weak gravity conjecture, but I think it's consistent. The problem is that these computations have led to somehow contradictory conclusions, and I just want to make sure I state what we found through these computations. So as I said, the computations are very complicated. I won't go into much detail, but I want to present how they work. So what we want to take is an extremal black hole in just Einstein-Maxwell theory, and put a loop of a particle with charge Q and mass M. Where is that? Charge Q and mass M, put it in a loop, and compute the corrections to the entropy to see if we find something interesting that could hint to the weak gravity conjecture. The way to compute the entropy corrections is to use sense entropy formalism, which dictates that we should compute not the, in order to compute the entropy, we can compute the corrections to the effective Lagrangian of the system in the background, in the near horizon of an extremal black hole. This near horizon is just an ADS2 cross S2 with some flags representing the charge of the black hole. And in order to compute this correction to the Lagrangian, we can do it using the heat kernel formalism, that is computing the word line Lagrangian of a particle, of the particle. S is the proper time on the word line of the particle, and K is the heat kernel. The heat kernel is quite complicated in ADS2 cross S2 with a background flags, but it has been computed by mathematicians and it has been used by physicists before. And we did the same, but this is how it looks like. So you have an exponential suppression, which is typical for heat kernels of massive particles. Usually you have an exponential suppression e to the minus sm squared. But what we find here is that the suppression is e to the minus s delta m squared. Delta m is precisely what discriminates extremal from subextremal from superextremal particles. So, and this is crucial to determine the IR behavior of this computation. So this will qualitatively change from subextremal to superextremal the behavior of the entropy corrections. So this hints that this might actually tell us something about this limiting of going from superextremal to subextremal. There's several other factors here. You have to sum over angular momentum on the S2 and momentum on ADS of a spectral density function, and we did this for fermions and bosons. I just want to point out that for fermions, this is the spectral density for scalars and for fermions. For scalars, there's a plus sign here, everything is fine. But for fermions, we notice that there's a minus sign here that tells us that there's a pole in the spectral density. This pole will make life very hard, and we don't know how to avoid it. It might have to do with the weak gravity conjecture cutoff somehow. I'll mention it later. So it's rather painful computations. You have to be very careful in taking all appropriate limits to compute the entropy corrections in area expansion of black holes. But the conclusions are the following. For super-extremal particles, that is when delta m is less than 0, the charge is bigger than the mass, what this computation shows is that you have Schwinger per production. There's an IR divergence, and this just tells us that your background will be popping out electrons and positrons, which is not surprising, but it's good that this computation already shows this. What happens if we tune delta m to be bigger than 0? Actually, what happens is that there is no significant corrections. And this is very hard to actually subtract from the computation, but it's a solid statement. Although, as I said, there's contradictory. Not everybody has agreed with that. I'm pretty sure this is consistent, that this is the result, that there is no significant corrections from sub-extremal particles. This is not what we would have liked to see in order to justify the weak gravity conjecture, but such is life. It seems like life is consistent in this setup. If you have exactly this extremal case, delta m should be equal to 0. There's two regimes of black holes where these computations can be performed. Super large black holes, bigger than any scale, received no logarithmic corrections again, so no problem there. For intermediate black holes, and by intermediate black holes, I mean black holes that are bigger than the Planck scale, so that we can control them gravitationally, but are smaller than the weak gravity conjecture scale. Which is interesting that the weak gravity conjecture scale shows up already here. We find an interesting correction, but it's a correction that does not become large or yield any problem. We don't see, I mean, it might be good for entropy counting arguments if you could reproduce this from string theory, but we don't see any argument where you could show that the weak gravity conjecture is violated or anything. This is all for scalar fields. What is tricky is that for fermions, as I mentioned, there's a pole in the spectral density. And because of this pole, these computations cannot be performed. We don't know how to do that if we want to integrate over all possible momenta on ADS. The only thing that we can do is to say there is a cutoff at this pole, and then we can do the computations. And if you put a cutoff, there's no problem. Of course, a cutoff of the weak gravity conjecture scale is precisely what the magnetic weak gravity conjecture tells us. However, well, this may be a sign of the weak gravity conjecture. I don't dare to say that this is the ultimate reason that there is a cutoff in this computation, but it's very suggestive that there are problems precisely at an energy which is precisely Q m Planck, the gauge coupling constant times m Planck. So these were some results that we got in this approach of trying to compute entropy corrections to black holes. So the second topic that I wanted to, I wanted to mention something about these other approaches that have been presented in this conference about other type of corrections, like not loop corrections, but classical corrections from integrating out massive neutral particles in this conference by Remen and Gary. It's very interesting. It's much probably more successful than the approach that we took before. And it tells us that as the black holes are becoming smaller, they become more super-extremal. Their charge becomes bigger, and then the objects that are more massive could decay. I just want to raise the question that I think it was commented during the talk during Remen's talk in the questions. Is like, what happens for microscopic states? This is the key question. If you want to do phenomenological applications of these conjectures, you need to address these objects have no effect. They are completely negligible in the low energy effective action. So if you want to claim any impact in phenomenology, you have to address what is going on in the sub-Planckian regime. Of course, this is way more difficult. But we need to understand if, as expected from string theory examples, things keep becoming more and more super-extremal. In this case, you have strong implications for phenomenology. Or if you could have a spectrum like this, we don't know why this should be inconsistent. If we want to apply the weak gravity conjecture to phenomenology, we should claim that this is inconsistent, but we have no idea, as far as I know, why this is intrinsically inconsistent. But this is something that we should try to address better. I don't know how to really approach it, really. But anyway, I just wanted to comment on that before moving to the zero form of the weak gravity conjecture. And as I said, I'm not going to give any new results, but I want to bring a topic that was very hot in the 90s, early 90s, when I was 6 years old. I remember lively discussions about this. And then it faded away, people forgot about it, and I don't think it's because it was resolved. I think it's because people couldn't really make much progress on it. It was a very exotic topic, deep quantum gravity, and very complicated issues, and what is more important, very important puzzles. So people saw problems that they wouldn't know how to handle, and in the end, nobody knew how to make progress. And now that we have the weak gravity conjecture and the Swampland program, what we are trying to do is to find problems in quantum gravity, things that we don't understand, and say, hey, perhaps the weak gravity conjecture solves this issue that we never thought about. Well, we have here issues regarding wormholes that could not be solved for a long time. Perhaps the weak gravity conjecture gives a fresh new perspective on how to address issues of Euclidean wormholes. So let me just briefly describe what these objects are, well, put them in context. So when we discuss the weak gravity conjecture for particles, what we discuss is, on the macroscopic side, we construct right and Nordstrom black holes, in particular extremal black holes, and their counterparts, we talk about elementary particles with charges, and we demand that there's some super extremal particle in the spectrum. We would like to understand the same in Einstein axion theory. You take Einstein theory and put an axion, which it's another gauge field, and we would like to understand what the macroscopic objects are. They should be some sort of gravitational solutions of macroscopic solutions of this theory, and the microscopic counterparts. This should be some type of instantons. In fact, these two setups are closely connected, and you can connect them in a simple way just by dimensional reduction, and you get that these objects relate to instantons, like black holes become instantons, and particles become instantons as well. One problem is that when you dimensionally reduce, basically if you take gravity into account, you not only get Einstein axion theory, but you get Einstein axion dilaton theory. And the behavior of gravitational solutions in the presence of a dilaton are much different than without the dilaton itself. So my approach here is that I would like to understand what the weak gravity conjecture is for axions without the presence of a dilaton, namely if I have stabilized dilaton at a higher scale. So when I address this question, what happens is the following. I just take some Euclidean Lagrangian of Einstein and axion theory, which is dual to Einstein plus a 2 form, and I want to understand the gravitational solutions to this theory. And the gravitational solutions include the following: is a throat. So it's a smooth solution in which spacetime has a throat that is basically supported by flux. That is 3-form flux on this 3-sphere that is on the throat. It's good to estimate what is the size of this throat. There is some n units of 3-form flux on this throat, and you just make a balance between the Einstein term and the kinetic term for the 3-form, and you see that the radius of the throat scales like the radius square is like n over f in Planck units. This is important when estimating what is the contribution of these objects. So you have a throat, and what happens when you go into the throat is that space opens up again, so you can have two disconnected spacetimes that don't talk to each other, or if you put the endpoints very far away from each other, you can have a wormhole that connects 2 points of the same spacetime. There are other solutions that I should mention in this type of theories that are singular but are also interesting. They might represent elementary instantons. one are called extremal instantons. I won't use extremal in this talk for them. I won't talk about this anymore, but it's good to mention that there are other solutions with that are singular but also representing instantonic effects in the effective action. But I want to focus on wormholes. So if you zoom out and consider wormholes as very small objects, you have that wormholes represent nothing but instanton anti-instanton effects connected by a bridge. So just like for instantons, you can do a dilute gas approximation and you can resum them and they exponentiate. However, the combinatorics is different because they are connected to each other. And what happens is that instead of a local action as instantons induce, what you get is a bilocal actions. The bilocality is because there's two ends of the wormhole. Now, this seems like very problematic, but Goldman showed us that this type of corrections to the effective action can be rewritten in a way that at least looks a little bit more local. You can rewrite it introducing alpha parameters, like an integral over some alpha parameter of this action that looks local, that has only one insertion of the operator that lives on the spacetime. So this is very interesting. This will tell that we have something that looks like a local theory, but what it tells us is that the couplings in this theory are not fixed. They are kind of random. In fact, if you take this approach, you have to integrate over the couplings of the operators alpha, which is something quite strange. It depends also on what the weight is here. It's an exponential suppression. This had some hope that it would fix some of the constants of nature. It also is very puzzling because it tells you that constants of your effective constants are not fixed. However, when you include this type of diagrams, also you are bound to include in your theory baby universe states. That means that not only I can go from a slice of space-time of space that is just one big universe to a one big universe, but I also have to consider, for example, something that is one big universe plus a bunch of baby universes to the same situation. And in fact, what the alpha parameters represent are nothing but the state. They describe the states in the Fock space of baby universes. In fact, it's very useful to think about it like as if this was the worksheet of string theory. And basically, these alpha parameters parameterize nothing but the background of, for example, gravitons that your theory is moving on. So the alpha parameters that control the couplings on your worldsheet theory, they are nothing but the parameters that describe the background on which your string is moving. So you can think of these alpha parameters as determining a metaspace in which your world volume is moving. This is quite useful, and it gives a good intuition. But it's puzzling that quantum gravity would predict, if wormholes are real, these alpha parameters. Now, the Giddens-Schrödinger wormholes are particularly important because they couple to axions. They are like instantons, they have a charge, and they couple to axions, and when they couple to axions, they generate a cosine potential. With a parameter alpha in front and e to the minus s wormhole, it's a non-perturbative suppression. So they are useful for phenomenology because they can stabilize axions. That's why they might be very important for phenomenology and for the weak gravity conjecture. However, you have to take into account that we can only trust wormholes that are large enough. That we have only considered Einstein-Maxwell theory, so we better stick to the effective theory that is low energy enough. And if you impose that they are trustable, that their radius of curvature is always sub-Planckian, you get, or below a UV cutoff, you get some constraint on the possible actions of wormholes that you can consider, and it means that these contributions are extremely highly suppressed, as long as your UV cutoff is below the Planck scale. So generically, they give negligible contributions. You can also still consider them as constraining some certain models, but it's, in general, quite hard to make phenomenology with them, just if you stick to this regime. In any case, as I said, wormholes are important. They stabilize axions, so they might have to do with the weak gravity conjecture. they are gravity solutions. So I think it's a very interesting topic, and there's many, many questions that we would need to address. And it's not clear, for example, what is the notion of extremality of a wormhole. We don't know precisely what the role of alpha parameters in the weak gravity conjecture setup would be. And if you combine wormholes and instantons, elementary instantons, you might argue that that's like the combinations of black holes and elementary particles, but we don't know precisely in a Euclidean setup what would be the processes that would be the analogous of black hole decay in the weak gravity conjecture. So, but as I said, there's many puzzles that were posed long time ago in the wormhole discussion, so it might be a good time to revisit them from the weak gravity conjecture perspective. Let me just mention a few puzzles. As I said, they lead to an indeterminacy of the coupling constants. There are some technical issues about IR divergences that could show up in wormhole calculations. But the most important one, perhaps, is more recent, is in holographic setup. It has been argued that holographically, wormholes should not exist because they don't have an equivalent in the boundary CFT. In fact, in the CFT, they could lead to all sorts of problems like cluster decomposition violation or violations of BPS bounds. So they seem to be very problematic, and people have been trying to actually get rid of them for a long time. There's been many speculations. Maybe we just don't understand quantum gravity at all. We just don't understand Euclidean formulations of gravity, so maybe just forget about wormholes. Maybe it has also been argued that maybe wormholes possess negative modes, so they are not saddle points of your effective action, so you shouldn't consider the contributions. Or maybe they are saddles, but they don't contribute to the path integral. So when you do a path integral, you have to make sure that all these may be complex saddle points, and you have to make sure that they contribute to the contour that you are trying to integrate over. So these are all interesting possibilities, but it's hard to actually get rid of wormholes, taking into account that they play a topology change, taking into account that they play a fundamental role in string theory, in 2 dimensions, and also in the target space. So I think it might be a good time to revisit some of these puzzles in the weak gravity conjecture, and I'm working on this with Arthur Hebecker and other collaborators, and I think other people in the audience are also. Some are interested, some just say, forget about this, it will be too complicated. With this I wanted to conclude. And, maybe just briefly summarize. I think the weak gravity conjecture has very, very interesting phenomenological applications, but we should make sure we understand what it is and where it comes from and how to precisely formulate it. Most of the arguments we have for weak gravity allow for loopholes, and they are very interesting. And these are 2 comments for 2 different communities. The Swamp Rangers, as Matt named them, should take loopholes seriously and try to close them. People doing phenomenology, just model building from effective field theory perspectives, should not take these loopholes very seriously. They just shouldn't take them for granted and say, oh, some gravitational effect will take into account of this, and I don't have to care about the weak gravity conjecture. And as I said, maybe it's time to revisit the issue of Euclidean wormholes, because it might give, we might actually either solve it or might give us some intuition about how quantum gravity works in the context of the Swampland. So thank you very much for your attention.
It's more a comment than a question, perhaps. So it's very nice that you revisit the wormhole problems. I just want to comment that it's a bit surprising that, given the age of this topic, that, as you know, none of the papers on the archive that investigate the stability of these Euclidean wormholes are correct, even the authors admit. So I'm just trying to suggest that, as you even had on the slides, that maybe the answer is very simple. And whenever they are macroscopic in size, there are actually too many negative modes and they cannot contribute in the path integral. This doesn't violate the weak gravity conjecture or the use in, say, QCD or axion cosmology, because it's exactly the ones with small charges which are therefore microscopic, that are needed in phenomenology. Sure. And imagine this is a true story because, well, preliminary calculations we have been doing over the years suggest it, but you don't have to agree. Then I think you both solve the problems or the things you have in phenomenology you still have, but you don't have any of the paradoxes anymore, because I think they are macroscopic wormholes.
Sure. Okay, that would be very interesting. So I agree that computations of negative modes, I cannot trust any of them. You can find claims that there are negative modes. You can find claims that there are no. I cannot trust any of them. Either way, I could the problem is that, as you know, there's the conformal factor problem, and it gets mixed up with, you have to get rid of it in any way in Euclidean quantum gravity, and all of these negative modes mix with each other, and you don't know how to handle properly in the negative mode counting, and it's a mess. So I agree that it could be that wormholes in the end are not real minima, but just saddles, and the question is where they will flow to. So what would be the endpoint of this decay of a wormhole? And if you're saying that it will somehow decay into elementary wormholes, what I don't know, it could be, but I don't know how it would fit. I mean, you would say that, first of all, you would have to actually say that there are some endpoint that in your theory you have to include elementary wormholes, right? Which would fit into the weak gravity conjecture. What is not so clear to me is how a very large wormhole with a large charge would decay into many of them. Like, the topology is very hard to change. I don't know. It's an interesting possibility, but.
In the holographic context, I mean, there's this nice paper of Jaffrey's who talks about traversable wormholes. How's it connected?
Well, I wish it was. Well, we are actually trying to understand a connection between Euclidean and traversable wormholes, Lorentzian wormholes. If there was such a connection, it would be really interesting, because you could connect with issues like ER-EPR, and it would ideally solve many of these problems. And I think it could actually also be related to Swampland ideas.
But you were trying to invest in connecting the weak gravity conjectures to Euclidean version, but you don't think there are any relation to the
It's hard to make a connection with Lorentz, and I don't know how. I hope there is one, but I don't, at this point I don't.